Hey guys, so in the last lecture we have seen few basic probability reliability basic functions. So today we are going to see few more functions. So we'll start so last time we have seen hazard function and reliability function. So today will start with MTBF. So what is MTBF? So MTBF is mean time between failures. So this we have seen, that is MTBF. So this is mean time between failures. So the reliability of a component or a whole system is measured by MTBF, that is mean time between failures. So it is the average time until a failure happens, and it is typically provided in hours. So to make it look more good or better in years, MTBF of 20 years means that on an average 10 years a failure occurs based on a large sample. So MTBF will be 10 years. So MTBF is a maintenance metric represented in hours, showing how long a piece of equipment operates without interruption. It's important to note the MTBF is only used for repairable items and one tool to help plan for inevitability of key equipment repair. So MTBF is basic measure of system reliability. It is the measure of reliability, and the higher the MTBF, the more is the reliability of the product. So MTBF is calculated by taking the total time of an asset is running uptime and divided by number of breakdowns that happen on over the same time. So I will write the formula. MTBF is equal to total uptime divided by number of breakdowns. So number of breakdowns, uptime divided by number of breakdowns. So to improve MTBF, we have following points which we have to take consideration, that is improve preventive maintenance process. We have to improve preventive maintenance process. We have to conduct a root cause analysis. Root cause analysis. So why there was failure in this product? So that is root cause analysis. Then established conditions based maintenance. It is establish condition based maintenance. So even though MTBF and reliability are different, you can very easily convert MTBF to reliability by using equation, that is e raised to reliability, that is function of time t is equal to e raised to minus t divided by MTBF. So where e is 2.7. Now the next topic is, that is MTTF. That is next function is MTTF. So this is mean time to failures. So it is a basic measure of reliability of non-repairable systems. So which system cannot be repaired. It is the mean time expected until first failure of a piece of equipment. So MTTF is a statistical value and is meant to be mean over a long period of time and a large number of units. So MTTF formula is total hours of operation divided by total number of units. So this will be in number and this will be in hours. So total number of operation hours divided by total number of units. The mean life function such as mean time to failure is widely used as measurement of products reliability and performance. So MTTF is equal to integration 0 to infinity r of t dt. So for exponential distribution MTTF, we can write is that MTTF is equal to 0 to infinity instead of r we can use this function, that is e raised to, so I can write just exp into minus lambda t into dt. So mttf will be, if I uh, go forward with this integration, so I'll get the value, it is 1 upon lambda. So mttf is a measure of the center of life distribution. For symmetric distribution such as normal distribution, mttf is the same as the median. So it is the same as the median. So we have seen mtbf, mttf. Now we'll see mttr. So what is mttr? mttr So mttr and variance we are going to discuss. So mttr, that is mean time to repair, applies only to repairable items and equals to the uh, total amount of time used to perform all corrective or preventive maintenance repairs divided by total number of repairs. Means how much time does it take to repair one item. So total time, so suppose there are 10 defective items, so each will have different time to repair. So total time taken by all the items, so total maintenance time divided by total number of items. So this will be in time and this will be in number. So this is the mttr. So mttr measures efficiency of repair programs. So this measures the efficiency of repair programs and the ability of organization to respond to repair issue, that how much what how organization is responding to its repair issues. So mttr can work as a factor for determining the repair or replacement of assets, establishing repair inventories, and for rental purchase decisions. Then next is availability. So what is availability? So it measures the fraction of time system is really available for use. So it takes repair and restart times into account. So mtbf, so that is mean time between failure, will be equal to mean time to failure mttf plus mttr, that is mean time to repair. So there is total mean time between failures. So reliability, so reliability will be mtbf divided by 1 plus mtbf. And availability will be equal to mtbf divided by mtbf plus mttr, mtbf divided by mtbf plus mttr. And variance var var will be equal to it is the measure of the spread of the life distribution. So variance will be equal to mttf. So what is mttf? So it is equal to minus infinity to infinity into bracket, that is t minus e raised to e is, that is function of time, whole square f of t dt. So for exponential distribution, the variance will be, if we integrate this, so we'll get variance is equal to 1 upon lambda square. So variance is nothing but 1 upon lambda square. So in applications we prefer using standard deviation, so that is sd. So standard deviation is equal to under root of variance. So since it has the same unit as t, generally the standard deviation is used together with mttf. So the standard deviation is used with mttf, so because they will have same formula. So these are the basic functions which we have seen, that is mtbf, mttf, mttr, reliability, availability, and variance. So what we have seen, that is mtbf mean time between failures, mttf mean time to failures, mttr mean time to repair, and uh, then availability, reliability, and variance. So this various functions we have seen today. And next, let's see an example, uh, so that we can get more clear idea. So let's see example. So, a electric component has a uniform failure rate. So, I'm starting an example. So, an electric component has a uniform failure rate of 0.0001 per hour. So, failure rate is given. So, that is mean time between failures. So, failure rate is given. So failure rate we denote as lambda, so that is 0.0001 per hour. So what is the reliability for a specified period of service of for 1000 hours? So what is the reliability for 1000 hours? So we have to find the reliability. So your failure rate, lambda, is given. So reliability is nothing but just minus e raised to lambda t. So our reliability will be e raised to minus 0.0001 into 1000. So it will be equal to e raised to minus 0.1. So the reliability will be equal to 0.9, 0483. So our reliability is 90.48%. This is a simple example which is asked. The second example we'll see. So for a particular item, if a mean time between failure, it is mean time between failure, mtbf, is given is 3000 hours. So what is the reliability associated with it for a specified service period of 100 hours? So for 100 hours, we have to find uh, what is the reliability. So reliability of 100 hours we have to find. So we know that mtbf is nothing but 1 upon lambda. So 3000 is equal to 1 upon lambda. So lambda will be equal to 1 upon 3000, nothing but. So we will, and what is the function of reliability? So reliability is e raised to minus lambda t. So r is equal to e raised to minus 1 upon 3000 into time into 100. So 0 cancel. So it is e raised to minus 1 upon 30. So it will be equal to r is equal to e raised to uh, so the answer will be, if we solve this, the answer will be equal to 0.9672. So will be equal to 96.72 percentage. So this is a simple example. We will see another example related to this. Example number 3. So suppose a product x has a mean between failure of 80 hours. So product x has mean between failure, mtbf, mean between failure, is equal to 80 hours, and mean time to repair, that is mttr, of 10 hours. And the product y has mtbf of 90 hours and has mttr of 4 hours, so which product has higher reliability? So we need to find which product has higher reliability. So what is reliability? So reliability will be equal to 1 minus failure rate per hour of operation, 1 minus unreliability, that is 1 minus failure rate. So 1 minus failure rate. So reliability, but what is failure rate? So failure rate is nothing but 1 upon mtbf, 1 upon mtbf. So 1 upon mtbf is, that is 1 upon 80. So for suppose for x, or if we are taking for x, so failure rate for x will be 1 upon 80, and failure rate for y, fry, will be 1 upon 90. So now reliability of x will be 1 minus 1 upon 80. so which is equal to 0.9875, and reliability of y will be 1 minus 1 upon 90, so which will be equal to 0.988. so therefore here as we can see that product y has higher reliability than product x, so the product y is more suitable. So this is a simple example. Now let's see in another example. So a ball bearing exhibiting, so next example number 4, a ball bearing exhibiting a constant hazard rate. So hazard rate is given. So hazard rate has a reliability of 90% of operating time of 1000 hours. So reliability is also given, so reliability is given, that is 0.9, and hazard rate is also given, that is 1, sorry, here hazard rate is not given, just reliability is given. There is 0.9% for time 1000 hours, so 1 2 3 1000 hours. Reliability is given 90%. So what is the average failure rate of a ball bearing? So we need to find failure rate of the ball bearing. So question mark. So we know that reliability is equal to e raised to minus lambda t. So now we know that lambda reliability is 9, e raised to minus lambda, and t is how much? 1000. So for 1000 hours. So we can, if we take log on both the side, so we'll get lambda is equal to ln 0.9 minus divided by 1000. So we can find the lambda. So lambda is nothing but 0 point, lambda is nothing but 0.00011, which is the average failure rate per hour. Now another question is asked. So what is the average, what is MTBF? Now we have to find what is MTBF. So MTBF is nothing but 1 upon lambda. So MTBF is 9090.9 hours. And another question is asked. So also, what will be the reliability of an item for an operating time? So reliability is asked for an operating time of, if this item is run for 1500 hours and 3000 hours, so what will be the reliability? So as we know the formula, that is e raised to minus lambda t. So we have lambda, we have t, so we can find, so this answer will be 0.8521, and here answer will be 0.7189. so same formula we can use. So this is an example where so many things are asked. Now we will see an another example. So example number 5. So the failure density function. So here density function is given of a random variable t is given as, so a density function is given, it is 0.012 e raised to minus 0.012 t. Here t is greater than 0. Then calculate reliability of the component and reliability for 100 hour mission time. Reliability in the form of function and for 100 hours mission time. So now what is the formula for reliability for a density function? So the formula for reliability for a density function is nothing but integration 0 to infinity f of t dt. So it is equal to 0 to infinity 0.012 e raised to 0.012 t. So if we integrate this, so we'll get 0.012, and integration will be e raised to, same as the function is e, 0.012 t, and this derivation, so this derivation will come in below, that is minus 0.012. so this will get cancelled out. So and the limits we have to put, that is the limits is from t to infinity, sorry. So the limits is from t to infinite. So it will be minus e raised to minus 0.012 t from t to infinite. So if we keep t, so it will be the same, and if we get so infinity, So first infinity will be 0, so the function will be minus 0 minus e raised to minus 0.012t. So this minus sign will go, so our reliability function will be equal to e raised to minus 0.012t. So for we have to find it for 100 hours. So for 100 hours we have to keep the value of t here 100, so it will be e raised to minus 1.2. So this is the answer for reliability. So this is example number 5. So we have seen so many examples. So in the next lecture we will continue with dispersion. So we will see dispersion. So thank you very much.